So I'm Yael Chrétien from the Prepare Institute. I currently realize a PhD with Prepare Institute in cooperation with software helicopter engines. My presentation will cover part of my research, and it will deal with near-stressor fatigue propagation of physically short and long crack in titanium alloy. Yeah, it's important. Thank you. So, first, why do we need to study short crack? Because they can propagate with higher growth rate than the one of long crack, and because they can propagate under the threshold of long crack. That crack propagation threshold is lower. It exists three types of short crack: microstructurally one, mechanically one, and physically short crack. We will focus on physically short crack because it allows us to use linear elastic fracture mechanics concept, and so to determine, to calculate delta key. Particular attention will be given to the determination of crack closure, because as you can see on this graph here, the behavior of 2D short crack is rationalized in terms of effective delta key. And you can also say that the relation of crack closure with the crack length up to reach the key opening of long crack. So the question is, how will we study this short crack? The industrial aim is to design critical components tolerant to the presence of short crack, which size is lower than the threshold of detection of the method of inspection. So my aim is to establish the non-propagation criterion. To determine it, we have to determine the long crack propagation threshold. We have also to measure crack closure using the variation compliant method. We have to propagate 2D short cracks at threshold and to determine the evolution of the crack propagation threshold with crack length. And so, to determine the non-propagation conditions. The tool used to determine the non-propagation conditions is the Kitagawa-Takahashi diagram. This diagram combines the fatigue limit in the domain of microstructurally short crack and the long propagation threshold in this third domain. We will focus on the transition domain here, which characterize physically short crack. Several models allows to characterize the curvature here of the experimental data. The first model and the simplest one in the LADAD, which inserts an 8-0 term in the square root. Zertmadia add an A star to this 8-0 in the square root. And we have also the Chapetti one, which takes into account of crack closure thanks to an exponential and an empirical parameter key. Let's move to the experimental setup. So I use CT specimen because it allows, it facilitates the crack closure measurement. And the material studied here is a B-model TACV, a titanium alloy used in compressor of aeronautical turbines. So my experimental procedure consists in 3 steps. The first one consists in propagate a long crack up to reach the threshold in order to obtain the smallest plastic zone at crack tip and to facilitate the crack closure measurement. We have to be very careful with the symmetry of the crack, so we have to control the crack length on the edge side of the specimens. The second step consists in progressively machining the crack rake and to realize crack closure measurement at each machining in order to obtain the evolution of the key opening respect to crack length. It is detailed on this slide. So here you can see a long crack. We remove first the red part and measure key opening for the delta C1 residual crack length. Then we remove the yellow part here and measure crack closure for delta C2, etc. As you can see, the determination of crack closure is quite difficult for small, short crack compared to long crack here. The transition is less visible. So I developed a tool proposed here, using the method proposed by Kim, which consists in calculating the delta prime, which is here, for example, and to deriving it 3 times in order to find a minus and to have a more accurate determination of the K opening. The last step consists in propagating our 2D short crack, which is here, of 0.1 or 0.2 millimeters. We choose the delta K between effective and nominal threshold as crack closure for short crack are limited. So we apply this delta K and realize a threshold. Then we increase the delta K and realize another threshold, etc. It allows us to obtain the evolution of the crack propagation threshold with respect to crack length. I will present some results only at room temperature, but we have also some results at 400 degrees. You can report to my article to see that. But I want you to really understand the methodology and the kind of result we can obtain with it. So here you can see crack propagation curve, quite reproducible, and we have a nominal threshold of 5.2 and an effective threshold of 2.5. Let's move to some K opening result. So you can see that the crack opening increased with crack length here up to reach the 1 or long crack. If we compare this to the data obtained from the machining, so this one for propagation and triangle for machining, you can see that they are quite similar. So we have to keep in mind that if we machining a long crack, we obtain the same results with propagated short crack. It allows us to obtain data in less time. We can remark also that the critical crack length corresponding to the transition between short crack here and long crack ranges around 2 or 3 millimeters. Let's see some non-propagation condition. So Okitagawa Takahashi for TSSV at room temperature with a load ratio R of 0.1. In the diagram, you can see experimental data and the models presented previously with this parameter. So we can see that the LADED and Zeus-Madia models are quite good, fit well the curve, the data. But for the moment, we only use LADED because it's the simplest and the best fit, the best compromise between the two. So to sum up, the obtention of a 2D short crack is 2D control. It's a quite difficult method, but we control it now. For crack propagation at high temperature, short crack propagation at high temperature is more difficult because we have to verify the crack length on each side, and when the specimen is in the furnace, we use DCPD method, but the sensibility is not sufficient to verify precisely the crack length, so we have to put the specimen in the furnace to propagate, to see the evolution of the DCPD, and then to remove it of the furnace to measure the crack length with a microscope and to re-put it in the furnace. So it's a very So we have to keep in mind that the evolution of clear opening obtained with machining is quite similar to the one obtained with propagation. So it's interesting to keep it for high temperature test because we'll spend less time to determine the data. We can also say that the critical crack length seems to ranging around 2 or 3 millimeters, but for the moment we don't know which signification given to this value. And the LADAM model seems to be the best approach because the simplest and because it fits well the data. So we have ongoing investigation are needed to propose a non-propagation criteria valid for several load ratio and different temperature. Thank you for your attention.
Thank you.